So here's the video where I explain how to use Mathematica to take a numerical Fourier transform and generate a power spectral density. The data that we're using is this piano data, and I import this from a Wolfram database, Wolfram being the makers of Mathematica. And you use this command here called example data, it's audio, and it's called piano. So we use that syntax there. And it gives this output here, which we can use to play the data, play the sound. And in this command here, what I'm doing is extracting the data points from that audio data. So this command here, audio data, extracts the points, and piano data is now an array of data. And in fact, it's two arrays or two columns of data, two vectors of data, one for the left, one for the right audio channel. Now, just to make things go a little faster, this is not a strictly necessary step, I'm going to combine those two channels together to make a single mono audio channel. So piano data 1 and piano data 2, that's the left and right channels, and it's going to take an average of those and generate a vector of data, which is just the single audio channel. If I want to listen to that, I use a command called audio, and I say audio piano data with this sample rate here. And this is the sample rate of the data which I imported in the first place. So I do that, and there's my mono audio. Sounds the same as a stereo, to be quite honest. Okay, now to plot the data, we use this command here, list line plot, piano mono data. So we're just plotting the data. And the rest of this stuff here is just to make the plot look pretty. And so here is our plot. It shows the amplitude, which is, I guess, some voltage measured by a microphone, and the time. And as we mentioned, you have some sort of signal that goes for about 3.5 seconds. Okay, now to the Fourier transform. So we know the Fourier transform is going to have real and imaginary parts, and we'll plot them separately. Now, here comes the tricky part. We know the x-axis is going to be frequency, but what are the units, and what's the maximum and minimum frequency? So here's how to figure it out. The number of points in the Fourier transform is the same as the number of points in the time data. And we know that the transform has positive and negative frequencies. Now, the maximum frequency you can uniquely identify is the Nyquist frequency, which is half the sampling rate. The sampling rate in this case is 22,050 Hz. Therefore, the frequency axis must run between negative half of this and positive half of this, which is to say from negative the Nyquist frequency to positive the Nyquist frequency. In other words, from negative 11,025 Hz to positive 11,025 Hz. Now, by default, when you take a Fourier transform in Mathematica and other numerical packages, I should say, the frequency axis does not run from negative to positive the Nyquist frequency. By default, it runs from 0 up to the Nyquist frequency, and then halfway along the plot, it jumps down to negative Nyquist frequency and then runs back up to 0. We can fix this, but we have to use a command to do it explicitly. Okay, so let's look at the raw Fourier transform. To take the Fourier transform of the piano data, we use the command Fourier. This takes the numerical Fourier transform. I'm going to call this data FT piano, Fourier transform piano. And then we plot the real part, and we plot the imaginary part. So here is the real part, and here is the imaginary part. Let's look at the imaginary part for the time being. And the axis on the bottom here is just actually the number of data points. It's running from 1 up to the number of data points, which is about 80,000. But in actual fact, what we know is that the first data point here is 0, like the DC term, the 0 frequency term, and then the frequency increases up to the Nyquist frequency in the middle here, and then immediately jumps down to negative Nyquist frequency, and then goes linearly back up towards 0. So what we want to do is, this should be 0 to Nyquist frequency, but all this data here, from here to here, needs to be chopped out and put on this side of the plot. So we use a command called rotate right to shift the 0 frequency to the middle of the plot. We take this data, we imagine it's in a loop, and we just rotate the plot. Then we can use a command called data range to specify exactly what the x-axis should be. And we know what the frequency limits are because we know the sampling rate and we know the Nyquist frequency. Okay, first of all, let's do the rotate right part. So rotate right, actually we could do left as well, it really doesn't matter. Rotate right, Fourier piano data mono, so this is the raw Fourier transform here. and then we rotate right by 78,412, which is the number of data points, divided by 2. Okay, so this is our redefined FT piano here. We're going to throw out this first definition and replace it with this one. And then we can plot the real and imaginary parts. What we get then is the real amplitude that looks like this. And I've now got a frequency in hertz. The way I get the frequency in hertz correct is by telling it that the data range here is from negative Nyquist frequency to positive Nyquist frequency. So I don't let it plot just the index of each point, I just tell it what the data range is. And so there's the real part now plotted in the way that we expect a Fourier transform to look, from negative to positive frequency with 0 in the middle and the real part, and also the imaginary part here. So what comes next is the spectral density plot. So to see the frequency spectrum nicely, as I've mentioned, the best way to do that is to find the absolute value, then square it and log it to give us the decibel scale. And so we take absolute FT piano squared, then take the log to the base 10 and multiply that by 10 to give it in decibels. And here I've just plotted from 0 to the Nyquist frequency. So I'm just telling it to plot from, so I tell it what the data range is. The data range will still be negative to positive Nyquist frequency, and then I tell it just to plot from 0 up to the Nyquist frequency. So just the positive part of the frequency axis. And so there we have the final result. Now, as a little bonus, I've also included this demonstration here that shows you how the Nyquist frequency comes about from sampling a cosine wave. And so here you can slide the sampling frequency around and just play with it and see what happens.